Will you introduce me, or will you introduce me, or?
I've done this before, Luka.
Aha, okay. Aha, okay.
Yes,
Good.
I remember just a few months ago, I think.
True, yes.
True,
Yes.
Yeah. But this time I prefer to do it a little less formally. So,
Sure.
Welcome to the Vardiya, Luka, to Neverland. Our workshop is called Neverland, and as you can see, we have. Can you see the setup at the back? There's a small.
I can, yes.
Arm. I can, yes. You are robot arm. You can
yes,
see
yes.
it.
Yes, yes.
You can see it. And
Almost.
there's a 3D printer.
Almost.
So, yeah. Exactly. Check out our Instagram account, so you will see here. So basically, what we're doing is we have a sandbox. In the middle of that sandbox is the robot arm and a compressor down below, and we 3D print nozzles that can manipulate the sand with like air jets with different paths and design. So we haven't done anything in terms of design and fabrication yet. We just started yesterday with our participants, our students. And now we're actually, yesterday we had time to go see the Biennale with the Arsenale, and today we're going to see the Giardini. And so tomorrow we're going to actually start with some action.
Okay. Okay. Are we now in Arsenale?
We are now at the Arsenale in the Turkish pavilion. Have you ever been?
I was many times there, yeah.
Very good, yeah.
But not this year.
One of the few air-conditioned sections, so we are pretty happy with our situation.
Great. You know what's important.
Yeah. Okay, so I'm gonna quickly, very shortly introduce you. So Luka Piškorec is a dear friend of both me and Selen and David. We know him from the ETH Zurich, actually. We studied at the same time at the Department of Architecture. We both did our master's degrees in the field. Luka was quick to find its way into the field of digital fabrication. He was, after graduation, he was leading the teaching program of back then DFAB, now grammatical research. He was giving students with elective courses, which challenged them with tasks that required them to plan, design the processes for robotic fabrication in architecture. He did it for 6 years, and after that, he got a great position at the Aalto University in Helsinki, from where he's now joining us. Yeah, I think Luka will give you a short introduction about what digital fabrication is. A little more theoretic, I guess. That's what we will discuss, but it's really up to him to in-depth understanding of what digital fabrication is, and then we're probably going to show you some examples, right? Or am I making it up?
Yes.
Okay.
I have two questions. First, I'm limited to an hour.
Yeah, ideally, yes.
Okay, ideally, yes. I will then.
Yeah,
I will try to be.
We still need to go see the Giardini today, so.
Okay, of course. I don't want to keep you off. One day. Second thing, how is the sound quality? Because there's a street here. Hope you can hear me well.
It's all right, but I think we have a small technical issue with our speakers here. They're like very. I'll see. I mean, you're speaking through your speakers, through your headphone speakers.
Yes.
Yeah.
Is this okay?
It's better.
This is better.
Yeah, it is somehow.
I mean, when I try to unplug.
Your beard is creating
Okay. I don't think this. I will hold it like this. Might be better. Okay. Cool. Okay. Okay. Because I don't think you will see my face anyway when I share the screen.
No, exactly.
Okay.
We're now turning our microphone off. Okay.
Yes, turn the microphone off. I have my phone open, so if anything is wrong, just send me, just text me because I will not stop when I start.
I'll get back to you from here. No worries.
Okay. Good.
All right.
Good.
Okay.
Cool.
Okay.
Thank you. Okay. Thank you, Orkun, for introducing me. Thank you for inviting me. So I'm calling you from a wonderful city of Helsinki, actually from my apartment. But I have a nice lecture ready for you. It deals with, there are kind of two parts, and they deal with kind of two little bit different types of projects. So the first ones I call tectonic-driven projects, and there's going to be kind of a short historical overview of some developments that need to happen in order to make the projects basically happen. So we're going to go all the way back to Renaissance, and then the second one it's going to be a bit shorter part called material-driven projects. So and also with a small kind of historical overview of changes that need to happen for us architects in order to make these projects happen. Of course, there is kind of a interplay between these two, and all the projects that I will show, I worked on them personally. Orkun worked on some of them, Selen worked on some of them, David also, so they're kind of very familiar to us, and there are very few that I'll point out that were kind of done at in our group in Syria before, so that was not part of, but that kind of we built up on that tradition. Okay, so I'll start sharing my screen. Okay, and good old PDF. Okay. You can hide this. Okay. So the lecture is called Digital Tectonics, kind of a discussion on emerging fabrication methods in architecture. And we basically start with this image, something that before I called it a measurement problem, but it's not really a problem. It is kind of it is something that is very inherent to our profession. So as architects and in general as builders and as designers, everything that we build in the real world, we have to measure. So at one moment it has to be measured. We have to kind of be able to relate our drawings to the physical world, and we do this through the act of measurement. So this is one of these measuring devices, specifically measures the verticality of the wall. Here is Sir Churchill using another measuring device, a string. So it just measures kind of the linearity of the wall. You can see there in the back. And in general, everything that we work with in the real world has to be basically measured before. But there's a catch. The material that we use is inherently imprecise. So there are tolerances that have to be dealt with. And with different materials, we deal with them in different ways. And basically throughout our history, so basically from building of the pyramids, or probably even earlier, but these are examples from the 60s. Basically, we were inventing not only measurement machines, but also building machines. So we were kind of inventing machines that help us to build. Usually they also dealt with this issue of measurement, or so they were at the same time measuring things. So in this case, this is a kind of a contraption that can build a straight masonry wall. Here on the left, you can see kind of contraption that can build rotating masonry columns or chimneys, and on the right, a technique that was borrowed from the boat building industry. You can kind of use a natural elasticity of the material to create a spline curve in physical space and use it as a guide for your brick wall, let's say. Or so these were all kind of very analog techniques. And then kind of something happened in the Industrial Revolution. So somewhere end of the 18th century, beginning of the 19th century, we entered into the Industrial Revolution, and then we started building really powerful machines that enable us to kind of build components. And all these machines had something in common, so they were very specialized. Usually, this means that they could do only one single task, So they had maybe 1 or 2 degrees of freedom. They could produce very standardized elements, and they would kind of do it very fast and very powerful. But in that sense, they were very constrained because their degrees of freedom was very low. And this lent itself very easily for mass production of parts. But already here in this example, you can see that once when we started to build things that are a little bit more complex than single parts, like for example cars, we had an issue, or so we had to kind of always employ human labor there. So this assembly of standardized parts had to be completely manual, because somehow we couldn't, our specialized machines couldn't accommodate this complexity of assembly in space and time. Luckily, since that time, we managed to bypass even that problem. So this is how actually every car factory today looks like. So these standard industrial arms were introduced back in the 80s. So they're with us already since, well, 30 years. And this is how your cars are produced. And in, for example, a Mercedes factory, it takes 4 days to build a car. 2 days out of these 4 days, the robots handle the car, and 2 other days still be handled by humans. And we are kind of trying to improve upon that. So maybe completely replace it with robot operation in the future, or the car industry is definitely trying to do that. What this enables us is to produce many, many cars that are all the same. So that's kind of this paradigm of mass production. And although this was tried in architecture, so this is an example from the 50s, the Levittown, Long Island, New York. So basically the first kind of mass-produced sort of American suburb. Although this was, again, this idea of mass production was tried also in the architecture scale, it was not very successful, and my opinion is also that it's never also going to be successful. So we will never build like this. This is kind of a, you know, days of the future past. So it doesn't work out of many reasons, specifically because architecture is very, very local in character, and usually the houses are kind of so big and so expensive that you want to kind of have them customized. It's very hard to drive the price down because of labor, because of the labor costs. But somehow, going back a bit into the past, we actually, in the very far past, we managed to build very differentiated structures. So here you see specifically vaults, Romanesque and Gothic cathedral vaults, where you can see that there's a very high differentiation of elements. And this is all built in stone. Before we had CNC machines, so they all have to be chiseled by hand. And these are some examples from the Eastern architecture. So somehow in the history we were able to create very differentiated structures. And this, of course, had many uses, not only for kind of cultural identity, but also for structural optimization and so on. But somewhere in the 20th century, we kind of lost this ability, and it's because the reasons are complex. But long story short, is because we lost these people. Also, we lost kind of craftsmen, because the labor market changed. We don't have these people anymore, and we cannot work specifically with stone in this way anymore. Everything that can be built, machines can be built fast and efficiently. Everything that has to be handled by hand becomes actually very expensive, and it's not affordable today. Then there's this kind of to jump back 100 years into the future. So today, of course, there's this promise of technology. The idea is, okay, we don't have these people anymore, but we have technology that can kind of help us to again create very differentiated and optimized structures, because we don't have to build them by hand. We have very smart machines. But this is just the promise, and this is our actor from a few slides before. So a standard industrial arm, it has 6 degrees of freedom. It means it can reach kind of, well, any point within its reach with any orientation. So and it's basically just a generic movement machine, so that means it just provides movement. But if you attach some specific tools on its end, it can basically replicate the hand of a builder. And of course, the whole trick is how to control these machines. Turns out that today our computers are powerful enough, our software is powerful enough that we can just do it, directly from a CAD program. So this is an example from a simulation of a Euro robot. I think that you also have in the now there in the room, and this is done in Grasshopper and Rhino, so kind of a standard CAD environment that architects use. And yeah, so then basically you can put whatever you want on its end, and kind of the robot can pretend to be an artist in that sense. You don't have to restrict yourself to kind of maybe two-dimensional operations. It can work completely in a three-dimensional way. So this is an example of robotic kind of light painting. Yeah, you can also use it for building. So when you can kind of place elements precisely in three-dimensional space and kind of sequence that, then you can sequence whole kind of production processes in that way, where elements are glued and then put one by one into the structure. So the idea is robots should be our friends, or so we have to kind of embrace them, and we should kind of embrace this technology. Yeah, there's another development that happened. So this was kind of the development of the machine, so of the kind of robotic arm that replaces the arm of the builder. There's another development that happened and basically started slowly happening in this like 15th century with Alberti. So this idea of drawing, or so how do we plan, draw, and design something? So Alberti was the first one who, in his book Dere Edificatoria in 1485, defined basically the role of an architect. Or so the idea was the architect is the author of the building, because he's the one who draws the building. Or before that, you had kind of master builders. So they were kind of anonymous master builders who kind of would coordinate the whole process of building, but they would never be named as authors. But Alberti basically said, no, architect draws the building, and he doesn't need to actually build it himself, because he's the one who drew it. So this kind of, in that sense, the drawing, architectural drawing, became, in a way, a vehicle for this authorship, basically kind of for this first design authorship. And of course, in that time, drawing was not. It was not just an artistic discipline, it was actually a scientific discipline. Also, there was a very specific way that you had to draw in order to get the perspective drawing. So perspective drawing would be constructed, very similar to how architectural drawings are kind of, they're in a way constructed with very, very specific rules. And of course, because it's these drawings are constructed, they're kind of very precise in that sense. So basically projections of three-dimensional space onto a two-dimensional surface. We use this not only for drawing buildings, but also surveying lands and so on. So we kind of co-invented also machines to measure and to draw. So a little bit related to what I was talking before about kind of measurement, machines that measure. Here are basically machines that enable you to draw very precisely. And this is actually a very interesting project from Alberti. So his kind of idea was that, so he basically, Alberti of course wrote before the invention of the printing press. So his problem was how to convey visual information reliably kind of through kind of ages. And he concluded, well, this information should be conveyed basically as a text, or so you should kind of have a written text, and it's easier to convey kind of, for example, in this case, monuments in Rome as polar coordinates in the text format rather than the actual image, because then if you have kind of the coordinates, you can just reconstruct the image anytime you need it. And of course, this is exactly how our computers work today. Also, our visual information in computers is stored as a string, so as kind of sequence of letters, of symbols that are then basically being displayed on a computer in just very, very quick way. But so kind of Alberti, he anticipated this idea of kind of digitalizing drawings or digitalizing processes. And here, this is kind of, again, connected to that, an example of something else that we invented basically in the 19th century with Charles Babbage, but Leibniz was basically already talking about that. So we invented something that I would call an operative script. Also on the left you have kind of a narrative script, so something, the script that is meant to be read by humans. On the right you have basically a computer code. So let's call it the operative script, because we can kind of still read it, or we can read the letters and the words, but this code is meant to be read by computers. and specifically executed by machines. So it's a form of a formal language, and this enables us, or this is, I would argue, a very powerful way to simulate the world, or to describe the world in a similar way how mathematics is a very powerful way to describe the world. Or so, in a sense, here a little bit kind of a dichotomy. Or so on the left you see the flock of birds, so kind of, you know, a lot of events happening at the same time. On the right you have kind of a musical score where everything happens in sequence. And when you work with the computer code, you have to work a little bit like a musical score, so you have to kind of sequentialize everything. And the question is, how do you sequentialize something that kind of happens at the same time? Or like on the left image, this is basically called discretization of space and time, and this is actually possible to do with code. And specifically when I teach my students how to kind of code, I teach them how to do exactly this. And this is kind of just one example. So this is kind of on the right, a discretized grid, so discretized space, but also this discretized time. On the left, there's a rule that governs how every cell behaves. And with this, you can actually just simulate fluid dynamics, for example. So we can use this discretization in order to simulate a world on a computer. And here we're not only talking about, you know, mathematical or kind of physical, chemical processes. We can go all the way kind of simulating societies in a sense. So we can go very, very high up, that kind of abstraction layer, abstraction kind of ladder. So here is the Christopher Alexander's pattern number 2 distribution of towns. Here on the right, you can see kind of the rules of how towns should be distributed depending on their size. And these rules are kind of so concise, or he laid them out in such a concise way that you could just directly script it. Or so you can script it, you can put it in the code, and you can actually simulate that. So something that he kind of anticipated, because of course in the 60s there were already computers, but you couldn't do such complex simulations. And of course, these techniques are used today in the gaming industries, entertainment industry, basically to simulating kind of, you know, virtual worlds and so on. But they're also used in scientific methods, so kind of numerical methods to simulate outcomes of experiments and so on. So somehow computers enable us to simulate the world that we live in. This is an example of what kind of code can do. Also on the right, it's Jacquard's loom. So it's basically a weaving machine. So you put in a code into it in the form of punch cards, and it basically weaves a carpet for you. So it's one of the earliest fabrication machines, and you can also claim that it's a first digital fabrication machine, because of course punch cards are nothing else but digital data. Or and on the left, it's you can actually see a carpet that was woven from 24,000 punch cards. Or so this was basically one of the first digitally printed image in a sense. So all the way to early 20th century. Of course, you can claim it was also very inefficient because it was analog, but of course we made it more efficient over time. So here on the left, you can see a CNC mill, or NC actually mill, so a numerically controlled machine. On the right, you can see a code for the mechanical part. So that's this strip that has that's kind of a punch strip, basically a digital code, and in the hand you can see a component that was fabricated. So in a sense, there's a relation between a machine that produced something, the code that was kind of generated and fed into the machine, and the actual physical artifact. Or in that sense, physical artifact is sort of a manifestation of the code that was put in. And not to go too much into this, but you know, when you talk about fabrication and specifically kind of digital fabrication, this becomes more and more relevant when we in the future, you know, when we will build things that are impossible to build by hand. In this case, this is kind of a castle on the top of a pencil. Or so this is something that would be very hard to build by hand. And when we talk about kind of nanotechnology and manipulation of material, basically the only way that we can build is through code, because we cannot build it by hand. We have to kind of employ machines, and the only way to communicate with machines is basically through code. Or so that's why code is important. Of course, architects work with, in a sense, projections, or basically approximations of three-dimensional objects. So basically with kind of 2D sections, elevations, plans, and so on. They are basically
again, approximations of three-dimensional objects that we want to create. And here we don't even kind of, you know, embed information of how something should be built. You know, this is kind of something that the builder brings on his own. But of course, today, especially if you work with modern CAD software like ArchiCAD and Revit and Rhino, you don't really work with approximations anymore. You work directly in a 3D model. So you just model three-dimensionally something on a computer. And of course, you know, this was kind of developed through time. So this is Sketchpad from the 60s, the first kind of CAD environment that you could use to draw in 2D. And when you draw on a computer, you're not bound to, well, at least not physical space. You're still bound to Euclidean space. Maybe you can kind of extend it to non-Euclidean space, but you have a lot more freedom to how you can design, or because you don't have to use straight rulers anymore. You can just work directly with curves, with splines. And that's why in the 90s, or basically 80s, when Gary and Eisman started to work basically with the computers, this directly influenced how their buildings looked like, or because they didn't have to draw manually anymore. That means they were not bound, or they were not constrained anymore by these manual drawing tools. They basically expanded the way that they could draw. So that's why also their designs kind of expanded, their design space expanded. And not only that we can encode geometry, we can also encode sequence, so kind of time series. Here you can see kind of every element has kind of a label on it, and basically you can basically every element knows its position in its kind of positioning in a sequence, or how it needs to be placed inside a structure. And this of course goes beyond just geometry. In a sense, your whole design becomes a computer code, to the point where you can embed procedures where your design, your design itself can know how it needs to be built. Or so, for example, you would load a file into one machine, and your design itself would kind of figure out. You would say, I'm loaded into this machine, so this is how I should be, for example, 3D printed. Or I'm loaded into another machine like CNC router. So I'm in a different machine now. This is how I can kind of, you know, build myself. So you can embed information also about building into your own design. So in a sense, you're working with very, well, not really intelligent, but let's call them kind of smart models, or so that are not only geometry, but they're also kind of a lot more information is dependent on that. And that's a little bit also the idea of BIM, although this goes, I think, even a bit beyond BIM. And now, why is this good? It's I would argue it's good because we don't have to draw ourselves. Just let computers draw. That means we can draw much faster, or we can explore possibilities that go way beyond what one single person could execute. Because you can just determine the parameters that you want to work with, and you let the computer generate 1,000 or whatever 100 examples that meet these requirements, and then you kind of start choosing between them, or in a sense as if you would have 100 kind of people that would kind of work for you. This can be done so this can be done through sort of laying out a structure. So all of these models are or all these drawings are in a sense connected to each other, but this is again done through code. So also geometry and sequencing, all this is kind of done basically through the same medium. And very often when there is certain regularity in how design is executed, there is also regularity in the code. So you kind of go through the code, and if it's ordered, that means that kind of something orderly will come out of it, and so on. So there's this bit of a relation between, say, how code is structured and what comes out of it in the end. Yeah, so you can work with kind of many different options, or and you can iterate through them very quickly, or you don't have to bound yourself to just kind of one that you managed to draw on that evening or so on. And of course, everything is parameterized, so it means these parameters can be changed on the fly in real time. And yeah, if you have kind of a production process that is also in a way digitalized, or digital fabrication process, then you can be sure that you can go kind of from the three-dimensional model to the kind of physical model in a relatively seamless way. So there's a lot of research done in that field how this can be done, and you can even design things that are beyond the scope of practical experimentation in that sense. But you could, in a sense, design it, and you can even perform structural analysis on these structures and so on. So you're not bound to physical space anymore. And there are, but there's the other part, or there are some projects that I will show at the very end that where material behavior is very important. Or so sometimes the material behavior cannot be directly simulated or anticipated, and this basically has to somehow, you have to kind of feed it in back into the kind of design process by using 3D scanners, for example. So we'll go through some of the projects that use that. For example, in this case here, you can see kind of a circle. That was the desired shape, but of course the little spheres show how the structure actually in the end ended up. So it's kind of it's called the low-res stochastic kind of 3D printing. Yeah, so you basically have to add one more element into this loop. So it's not only you have a kind of your designer behind the computer, it's not only having a fabrication machine, so kind of a mechanical builder, but you also need eyes, or so you need 3D scanners or cameras that enable you to connect what happens in the real world with the material and kind of connecting it back into your virtual world in that sense. So I will also not use the term virtual a lot, because I think it's a very outdated term. Because we are kind of really talking about processes that are very, very physical, but that we control through kind of programming through computers. So there's very little, let's say, virtuality in there. Okay, so I think I have half an hour. I'll go through the projects now. So tectonics driven projects. I will first start with this robotic masonry. I'll just kind of run through them. So a lot of these projects are already quite old, so they are kind of 10+ years old, and the idea is that there are these kind of two paradigms of digital design, also manual drawing and modeling, which still a lot of offices to this day use, and the other one is kind of generation through instructions. So all the projects that I will show you use this second paradigm. And also when we teach our students, we teach them the second paradigm, and I think you will also learn the second one also in the workshop that you're working on. So that is kind of the not really the present yet, but kind of trying to kind of push it into the future. So we tell the computer, basically we don't draw ourselves, we tell the computers how to draw something for us. And specifically when we work with masonry, we start with physical constraints. Also, it's not like we are reinventing how to build with brick, so we are kind of building up on the whole. We're building up on the whole tradition of kind of brick building in thousands of years, but we formalize these rules. So this is how you would get it in a kind of a book on masonry, and this is how we kind of formalize it in a sense. Okay, placing elements in a layer, we have a position and kind of rotation, and they're not allowed to overlap, and we have to somehow put them so that they're kind of self-stable in this. In every iteration. So in that sense, we just kind of formalize these rules kind of from the books. We formalize them so that we can use them in our processes. We do a lot of hand experiments, and in the end, this code doesn't really have to be very complex. So this is like, I think it's maybe like 20 lines, and it already can produce quite kind of complex outcomes. So here specifically, these are kind of brick columns. And by just kind of changing the parameters, we can change the expression, the geometrical expression of this column. Of course, they're all just made out of layers. So there are kind of few ways to build it. So you don't necessarily even have to use robots to do this. So this is one of these kind of measuring machines. So there's basically, you can see kind of on the right, there's a mirror, and you can see kind of a small projector basically projecting the image of these layers onto the model. Also, you can kind of use rather analog techniques, but using kind of this measuring device in order to build very precisely, also kind of replacing the robot. These are some of the outcomes, or how these models can be then built. Or yeah, you can kind of completely bypass a manual process and say, no, once when you have everything in a computer, everything is in a way the same format. We just kind of feed in this information to the robot, and the robot can kind of execute it. Or now you have to notice that this is a little bit different than when you just do a three-dimensional drawing. It is not necessarily trivial to directly translate it into instructions that the robot can read. But when you script your model, then usually this information is already embedded in your model, or so you don't have to really do much extra. You just have to kind of use the same information. So this is really this kind of idea of kind of going from this analog way of drawing, even if it means on a computer, to generation. Also, these are some facades made by kind of Rob Technologies and Keller Ziegeleien from Switzerland, for whom Selen worked for quite some time. For example, these are this kind of facades that you can kind of create using their software, and of course they have the robots in-house that you can just kind of use to produce them. So it was 2008 was the Biennale, Venice Biennale, so exactly 10 years ago when they kind of built installation in the Swiss pavilion. Yeah, so this is the machine that they have, and these are the elements that they produce. They can be kind of shipped all over Europe. They're of course glued. They can be used as kind of acoustic shredder, diffusers, or as a kind of a decorative facade in front of the buildings. Yeah, this was the structural oscillations in 2008. So in Venice, so the idea here was basically to add structural stiffness, so stability by kind of curving the wall. Otherwise, using just a single layer of a running bond is not a very good strategy to build very high. So in traditional brick masonry, you never see a running bond that goes beyond 2 meters or something, or beyond a meter for that matter. There's always a kind of support behind, but here you don't need any support because the curvature adds stability. Okay, and this was then also used in actual building projects by Gramazio Kohler architects all the way back in 2006. And this is an example from Shop Architects from US. There the process was a little bit more manual, but kind of they worked with molds. So there are more ways that these structures can be produced. So you can use kind of sort of guides and mock-ups and so on to produce them. And this is an example actually from China, because they do build a lot. Okay, so we can go back a little bit to this kind of academic setting also. You kind of create, usually we use something that is called pick and place. So robot goes, picks up a brick and then just goes and places it somewhere. But you can also build these kind of small, let's say, holders that are kind of magazines where you can put in a stack of bricks, and then they can be deposited. These bricks can of course be very differentiated. They don't have to be same, or they don't have to look like a brick, but they can be kind of highly differentiated, but still kind of standardized components. You can even work, with kind of dry stacking, almost like kind of playing with, the house of cards. You can also think about kind of, okay, what are these machines that are building this? So they can maybe also be moving around, because then they can enter a construction site and be actually useful. So we don't have to we don't have to prefabricate these walls. We can build them in situ. And this was the last project done last year, actually with David, 2017, where you have this kind of ecology of robots where big robots have this kind of stack of bricks, and the small robots are sort of assembling these stacks. And this was done in Zurich, so kind of a sort of a large, let's call it the 3D printed structure. This is a small robot, Euro 5, kind of assembling the stacks, and then kind of the big ones are taking the stacks, and then this is just kind of dry stacking inside the hole, so we can disassemble it later. I forgot how many elements were in there, but this was unglued, so we could just disassemble it later. So the idea is you can think about this as kind of just a very large-scale 3D printing. And yeah, not to go too much into this, but there are of course companies that do this on a commercial scale. So Construction Robotics from the US, and Hadrian X, so building the Hadrian's Wall, where the idea is you have a kind of a very long reach and kind of a very sort of smart actuated component at the very end of this crane, and then you can kind of brick or you can kind of build very, very quickly. So this is actually a service that is already being offered in the US. So kind of completely robotically built structures. Okay, and just a kind of small recap of this part is, I kind of mixed them up a little bit here, but basically there are two main developments in robotic masonry. and in general in robotic fabrication is the first one goes in the direction of automation, and the other one is differentiation. So in a sense, automation is interesting for companies that want to make money, because if you can build something faster or quicker, it costs less, because manual labor costs and machine time costs. But we as architects should not be primarily interested in that. We should be interested in differentiation. So so it turns out when you build with robots, you have a lot more freedom in how and what you can build, because you're not, the machine does not really have to measure every position of every brick. A human needs to do that, but the machine doesn't have to do it, because these robots have kind of a sense of absolute space. Because of this, in a sense, shape comes for free, and the only thing that we have to supplement is basically planning of this shape. And in that sense, we have to really work on differentiation. So in that sense, this is a little bit of what's the name? I forgot the name. It's kind of it's a very strange image, because you have this very, very high-tech building platform, but it's building houses that have, straight walls, which is a little bit strange. You would think that once when you have robots that built, we don't have to constrain ourselves to straight walls, because the robots don't care if they build a straight wall or a curved wall. So in that sense, in the future, our houses will also look very different because of the differentiation. But somehow the industry is driven primarily by automation, the same way Facebook is, not driven by, Facebook is driven, for example, by ad industry, not by anything else. So, okay, I'll go through these projects, the last batch of projects. There are going to be quite a few of them. So spatial aggregations was a project we did in 2012. The idea was to use robotic fabrication to place linear discrete elements in space, but kind of freely in space. So that means we would use round profiles, so we can get these very generic joints. So if you just achieve proximity, you can basically connect two elements together. In this small scale, we did it with kind of super glue, kind of krill sticks and super glue. And again, because the robot doesn't need to measure every position in space, it can kind of determine, or it can kind of directly relate spatial angles from a CAD model to the physical space. And specifically here, we use the kind of technique of interpolating some elements in order to stiffen them. So there was kind of a combination between human labor and kind of robotic labor. But these are kind of some of the outcomes then. So some of them you can see regularity. For example, this one is a surface. This one is kind of two rings put on top of each other. This one is like a kind of repetitive tower, and so on. So again, if you would look at this just as a kind of purely model building technique, it might become really hard to build this by hand, or because these angles would be really hard to kind of measure in space. But the robot kind of bypasses that problem. And even here you can see it looks very complex, but it looks complex because the elements themselves, they have, of course, thickness, and in physical space they have to bypass each other. So when they start bypassing each other, they're a little bit extended. It kind of creates this kind of a chaos. But all of these elements here are triangulated. Actually, David worked also on this project in 2012. So you can see these kind of cells, like square cells that kind of repeated over and over. And this was done in a kind of a large scale using a large KUKA robot. Elements were kind of pre-cut and then assembled into these stable spatial modules, which were then kind of built on the construction site. Yeah, so there's a bit more manual labor in this project here, but you can see again the cell here. But we tried to improve on that as we went along. So shifted frame took this idea of spatial assembly a little bit further. So the idea was to use a less generic joint. So to use just a square profiles and to use orthogonal directions. So we had only 3 directions. And, you would kind of think, okay, 3 directions, square profiles, in this case, specifically, all elements had the same length. You would kind of think, but that's going to be super boring. They're all going to look like cubes, because there's not much that you can do, not much else that you can do if you're only allowed to use a right angle. But turns out that there are certain things that you can do. So you can start kind of interpolating them and create these kind of structures that that are in a sense redundant, or so they kind of start becoming space filling, or so also not very optimized, but in a sense where structure starts to kind of fill up space. I will not connect it directly to deconstructionism, but the idea is that the structure is not on the boundary of the space, but it kind of starts to fill up the space itself. It starts becoming the space itself. So these were projects done in the small scale by the students, and then we went into one-to-one. Actually, Selen worked on this project, and Orkun actually also worked on this project, if I remember correctly. Yes. So yeah, the kind of big robot, cutting the elements, and a lot of connections we do by hand. So that we don't automate the whole process, but because the project is only 4 weeks, we had to speed up somewhere. So connections are then done by hand. And again, we create these modules that are kind of self-stable. We move them around, and then we can assemble them in a whole. You can see small wheels on the bottom, so you can move them easily around. This actually in front with the screwdriver is Orkun. Yeah, so this is how it looked like in the end. Here, of course, we use the rectangular profiles, not the square ones. Yeah, all these projects, they were actually quite short-lived, so they had to be dismantled within a few months of their construction. But yeah, complex timber structures, again, went a step further. So we said, okay, we don't use orthogonal directions, we use kind of any angles, and we cut the elements at the end. So every time you do anything to an element, every time you kind of cut it or somehow, every time an element becomes more specific. So for example, you go from a round profile to a square profile, or as soon as you do a single cut, you're basically embedding spatial information into the elements. And that means that what the robot can kind of give, or what the robot can kind of put into the structure is kind of less. Or so the robot then has less freedom of determining basically or of placing the elements inside a structure, because some planes are just defined already. So here specifically there are two robots. One of them is cutting, the other one is holding and rotating the piece. By combination of these two angles, you can kind of get basically almost any spatial angle you want at the ends, and then the elements are kind of being put into the structure. So when I talk about kind of specific joints here, you can see that at least one angle is already defined, because the plane to the end of the other element. So in that sense, you already embedded at least part of the spatial information. You constrained the freedom, but of course there's still, the position is still not fixed through this operation. And these are some of the outcomes. There are some operations that would fix kind of all the geometric freedom. So for example, a lot of CNC milled joint projects that you see out there in projects, they basically work in a way that they constrain completely the freedom of these joints. So that means you don't even need a robot to assemble them, because there's only one way that they can be assembled. This robot here, yeah, this is sort of its reach, and then we decided to do this. It's called the kind of mushroom piece. So again, very similar in one-to-one. You kind of cut it with the big saw. We kind of pre-drilled it, although this was less successful. But basically, in the end, you can connect the elements together. And this was only 99 elements, so not so much. And when everything was working, it took us only 2 days to build. But it took us like 3 weeks to set everything, so it kind of works. So, and the trick here was that the robot stayed put, and we could actually rotate. We could rotate the piece around the axis. So there was kind of 3 axes of rotation, or 3 axes of symmetry on this piece. And when you look at it in the detail, it would seem as if, if you look at the triangle joints, you would think, there's a kind of a mistake there, because they don't seem to they're not flush. But of course, this is a geometrical consequence of the fact that you're trying to approximate a doubly curved surface with straight elements. So this will kind of always happen. This is impossible to avoid unless you use curved elements. So that's why on the upper part, you can see that triangles are a bit more flush, and on the lower parts they are less flush, and this is because, of course, in the upper part there is less curvature, and in the bottom part there's more curvature. So in that sense, even though you cannot really see the surface because the surface is kind of mostly empty, if you just look at the way the joints are constructed, like in detail, you could kind of deduce the amount of curvature in that. I have the mouse. You can determine the amount of curvature in that point in the surface, which means that you can kind of read how the whole surface behaves through looking just at its detail. And this is something that I would call this kind of structural honesty, and it's something that we as architects should maybe kind of aim for more. So you have kind of an honest structure that is kind of revealing itself in the detail also. Okay, so this is the last one out of these projects. I think I have still 10 more minutes. Last project that was in its tectonics-driven project. So this was the house that we did, a project we did for the first MS in artificial digital fabrication. So program that David is now running. So this is the first year that we did it, 2016, and kind of the first big project that we did with those students. So the idea was we wanted to kind of combine a lot of the techniques that you saw just before, and so we wanted to have kind of a complex structure, meaning walls, slabs, roof. So not only to have kind of these layers, plus we wanted to have a facade. So of course, even this whole piece or even this whole house could be kind of what we call chunkified, or so you can kind of cut it into chunks, and these chunks could be fabricated one by one or on the robot. So again, we use basically Rhino CAD environment with Grasshopper, kind of custom built components, big CNC saw, and then elements would be kind of positioned where they should go. So there's also hierarchy of elements, so kind of larger beams, thinner beams, and so on. So I think there are 3 different thicknesses, and connections then done, in this case, properly by hand. And here you can see on the right there's kind of a slab. So the pieces of the slab on the left, this is a roof piece. It's kind of inspired by the kind of boat building technique. So it basically looks like a hull of a boat. And yeah, here we also wanted to keep the piece for a bit longer, so the house for a bit longer. So we had to clad it in order to protect it, and we used just standard cedar shingles. Once when the chunks are produced, they can be mounted on the construction site relatively quickly. So also the idea is the more time you can save on the construction site, everything becomes cheaper, because somehow building on the construction site is way more expensive than building in the fabrication hall. So this is kind of the business model of a lot of these companies that work with prefabricated wood elements, for example. This is the slab from the bottom floor before the roof is put on. So there's kind of a light coming through, and yeah, this is before the roof was put, the upper floor, and this is then the final roof. It looks kind of like a Viking boat in a sense. And yeah, so here, this is this kind of upper floor. This house is actually still in Zurich in the old botanical garden, still there. So if you ever go to Zurich, you can go and visit it. And here the idea is that there are these kind of modules, which are sort of like trapezoidal kind of shapes that are stiff because they're triangulated, and even when they are deformed, they are still stiff because the deformed triangle is still stiff. So in a sense, and if you assemble a lot of stiff elements together, you still get kind of a stiff structure. So this is kind of the, let's say, the idea behind the kind of how the forms should relate to structure or to construction. Yeah. So this was a DTH, but now it's in the old botanical garden. I have 5 minutes, I think. Procedural wall. So now we go to this material-driven projects. There are only 3 of them. Try to run through them very quickly. So the idea is, what happens when we now, when we don't work with wood, when we don't work with brick, with metal, when we work with material that whose behavior we cannot directly simulate. So for example, with aggregate material, in this case, sand. So the way that you get these sand dunes here is just by modulating the speed. Also, when you have kind of a sand bump, it means we move slower. When we have, when there's kind of a valley, this means that the robot moved faster. So it deposited less material. And by changing the phase here, so this shifting the phase, you can kind of get this interplay of these kind of valleys and ridges. So you're basically not designing directly with shape, you're designing with these speed curves. So there's a discrepancy between, in a sense, your kind of, you know, design tool and what you get in the end. You spray it, so here specifically we use it as forms for latex, forms for concrete. So you would kind of spray latex on top of them, and you would put just concrete on top, and then you can remove the latex, and you would get these kind of casts. So because the sand which was used as the form can be reused, this was basically a way to kind of way to use a reusable formwork, or so in a sense you don't have to throw away the material after it's used. You can reuse it. Here maybe something similar to what you're going to do in the workshop. So here we just kind of move the sand around. So again, we designed basically these move curves, and this is the, you know, the shapes that we got. So we didn't know how this will look like before we started, but because we could prototype very quickly, we can kind of embed this into our design process. But our design models were actually very simple, so they were just kind of design moves, and all the complexity didn't happen in the kind of physical world, in the actual material world. And yeah, this one was maybe a bit more straightforward, because you use this red sand that could be very easily compacted, and we create this kind of tensor field of kind of, you know, stamping trajectories, and this is the negative, and then here you can pour concrete directly on it, because this red sand is hydrophobic, and then this is the positive that you kind of get. So this negative kind of valleys became sort of positive shapes. Yeah, so it turns out when you work with sand and with this very controlled robotic kind of movement technique here, it turns out you can, you know, even in this kind of very messy environment, you can create very, very regular shapes. This is actually my favorite project ever. 2014 remote material deposition. The idea was to create a 3D printer that has uses ballistic deposition of material. That means we deposit from a distance. So, you know, usually your 3D printer needs to be bigger than the piece that you're printing. So that's the case on the left. But on the right, the idea is, well, maybe I have a very small printer, but it has a very long reach. Or in this case, we can kind of shoot out the material. So, so there's this certain inversion. So we can have actually very small machines that build very, very big. And here you can see Sela, former student of ours, behind the computer, connected to the machine that is shooting out this kind of Velcro modules, and on the top you can see a small Kinect camera. So a Kinect camera is scanning what's happening on the field and kind of feeding that back into the computer, because, you know, I call this stochastic building, because you don't know really what's happening, because, you know, there are ballistic curves, but there's kind of air resistance, the profiles that bounce off, and so on. So there's also something that's called a spread, so the material kind of spreads in a very specific way, and we did this then in 1-to-1 with clay. So this contraption fits in the back of your truck. So in that sense, it's really mobile. And there's a kind of 6 scanner on the top, used for 3D scanning. And we tried to shoot concrete, did not really work. But in the end, we used clay because it kind of retains its consistency long enough. And here you can see that it's actually a ballistic curve when you shoot it out. So this is shooting out some light modules. Yeah, so these are basically more or less all ballistic curves, so meaning parabola, if you don't take into account air resistance, which means you can calculate more or less where it's going to land, but you can kind of use 3D scanning to check, you know, if you're trying to achieve a wall of a certain height, so you're always checking if you actually reach the height or not, and you're always correcting the strategy. In the end, we really scanned everything kind of to get kind of all the layers out. And here, this is a scan from the top. You can kind of see there's a certain spread, but it's kind of polar, spreading from kind of bottom middle point. That's actually where the shooting machine walls are. So the further you shoot, the more imprecise you get. So the walls get thicker, and there's kind of a spready direction, or that radiates in a polar fashion from the robot in that sense. And this is how it looked like in the end. I think it was 15 tons of material, yes. It was actually 15,000 projectiles, something like this. So it took us 3.5 weeks to print. No, 3 weeks only, yeah. to print this amount. It's also very crappy summer in Zurich, so it was very wet. Okay, so this is the last project. I think I almost already did my time. So Iridescent Sprint is the last project that I will show you. And here the material is thermoplastic polymer, specifically ABS. So you probably saw these projects, you know, all over. So the idea is you free print with plastic, but you don't print in layers, you print in space. And yeah, you can kind of extrude in space, and because you extrude hot, then you cool it as it comes out, you can solidify this material. Actually, this project was then continued by David and worked a few more semesters with students, so he probably now has even more knowledge than me. This, I was kind of doing this for the first time back in the 2015. Yeah, so you kind of really push the boundaries of what can be done. So there's also a little bit kind of helping by hand but or kind of, you know, a little bit manual kind of digital sort of building, but cool thing is that you can print in space. Or so this kind of number 8 was actually printed like this, so no supports. Yeah, you can use something that, you know, we call functional grading. So you can print material that kind of has a very regular shape, but you change the distribution of the material inside in order to have different performance of the material. In this case, kind of a, you know, kind of a beam action inside, or this was actually printed like this, so we can actually print really long or really kind of big kind of consoles. You can work with hexagons, rectangles, triangles, of course, and so on, and you can kind of use the techniques from bridge building industry. So here specifically, you can kind of pre-print kind of a cable and use it as a support and start kind of printing on top of that. And then as soon as you connect the first set of this tetraders, they kind of, you know, starts to basically carry as a beam and self support. So the idea was here was kind of how to build basically in space without supports, and turns out there are a lot of techniques that can be employed to do that. And then we did this in kind of one-to-one, but here we introduced color. So we used the gradually pigmented filament. So the filament was changing color between blue, yellow, and white, and then of course in between that is green. So you could actually follow the sequence, or because in the previous examples you could maybe only determine the direction of gravity, but here you can actually determine the sequence because you can kind of follow the color more or less. So you can see how it was printed. Again, related to this honesty of the construction, also somehow looking into the detail of the piece, it kind of tells you a little, basically tells you a story how it was built. Also, it kind of tries to reveal even the sequence or temporal sequence, which is something that we found very beautiful. And yeah, in the end, it was exhibited in Palais de Tokyo as a gallery in Paris. And that is actually it. And I'll just finish with a quote from Marshall McLuhan, who's basically the father of kind of media theory. Worked mostly in the 60s and 70s, and he's a very quotable person. But he wrote somewhere at one moment, as technology advances, it reverses the characteristics of every situation again and again, in the sense that the age of automation is going to be the age of do-it-yourself. So he already kind of back in the 70s kind of anticipated, you know, in the 70s it was all about automation, you know, everything's going to be mass-produced, houses, cars, like planets, whatever. But he already then anticipated that this will probably change, and that kind of, you know, all this technology will enable us to build actually in a very customized way. Well, maybe also Star Trek anticipated this, you know, with replicators. With a replicator, you tell it, you know, tea Earl Grey hot, you get kind of your tea the way you want it. So maybe it was not so radical, but basically this is a little bit the age that we are living in now, where we are kind of moving into this kind of mass customization paradigm by using basically the same, or this technology that was before used for, you know, kind of this for mass standardization. Or so it's all about kind of how you employ the technology that is available for you, and that's kind of, I think, the very big role for. I'll just turn off my screen share. I think that's a very important role of architects and designers in general. So to be comfortable with the technology and to really use the technology in a way that it facilitates your work, or so your design work. I mean, I'm just going to conclude here, give you one example. You know, look at, for example, how Apple as a company designs. You know, Steve Jobs comes in a Toshiba factory, and he sees they produce like the world's smallest hard drive, and he asks them like, "Wow, what are you going to use this drive for?" And they tell him, "Oh, we don't know. We just made it because we could, and I don't know, we think we can maybe put it in a very small laptop." And of course, that was the first iPod used this Toshiba hard drive. So there was so you had kind of technologists that invented something that they didn't even know what to use for, and then you needed kind of a very creative mind, basically a designer that says, no, this is the time where this will be employed, and we will use this to kind of revolutionize the way we listen to music. Not to mention the second revolution that Apple did was with your phones. In a sense, no keyboard, it's all touchscreen. Also, and it's not like we didn't have touchscreens before. We had them before. It's just that this was the first time that it was employed, in a way that it can actually be used. So this is, again, just to conclude, the role of architects and designers and inventors to basically use technology that already exists there, and just put it into good use. Otherwise, we will make ourselves irrelevant in the very, very near future. And there's even a chance that we might go extinct as a profession if we don't embrace this way of thinking. Thank you very much. I ended up on a very pessimistic note.
Thank you, Luka. You can hear us right now, right?
Yes. Yes.
I have to press it, and now you can hear us.
I can hear you.
No.
I can hear you.
Now you can hear us.
Yes. Yes.
Say yes if you can.
I can hear you.
Yay! Okay. Thank you very much. I think you mastered this presentation by far, and it's been an amazing introduction to the topic, and thank you for taking the time. All right. Apparently, we had to manually switch to ourselves now. So yeah, maybe our students or anyone from the crowd has some questions. Anyone?
Do you hear me, Luka?
I do.
Okay. Well, first, thank you for the very inspiring and insightful presentation. I want to ask a kind of broad question. And I know you and Orkun and David and Selen are kind of deep in the rabbit hole of this research and fabrication. But what is for you the overarching project of this research that has started in, I don't know, 2005 or something with robotic fabrication? And you hinted at some stuff, for example, by showing at the introduction of Deleuze for the folds. So there might be a relation to a Baroque kind of attitude towards design, where it's we're talking about an operative methodology instead of a creative one. And about your last note, it also sounds like this design is very driven by technology and very interested in actually the technological methods, and maybe a bit less about the design or form or aesthetics.
I'll try to interpret your question now. It is true. It is. Let's say our research is very technology driven, but the technology is not. That's not the main. That's not the main goal. Those are just the means. I mean, I hope I managed to convey, in a sense, that as the technology changes, we have to change the way we think and the way we design, because we have to kind of embed, or we have to embed it in our work. Otherwise, as I mentioned, we risk make ourselves irrelevant. One good example is, for example, the 3D printing in general. The whole 3D printing revolution. Just to constrain it to this, now we have 3D printers, and we have them in small scale, but we also have them in larger scale. We can almost build or almost 3D print buildings. And actually, Marshall McLuhan is a great person to quote here, because he basically paraphrased more or less Gottfried Semper. There's this Gottfried Semper had this Stoffwechsel theory, or the idea is that when you change the material that you build with, you tend to retain the shapes that you had before, because somehow the shapes became the means in themselves, but they were usually always derived from the technology or from the material. Marshall McLuhan says the same thing, but in context of technology, that when we change the technology, we tend to kind of use the similar way of thinking as technology before. For example, web pages. In the first web pages, they were basically like books. They had a page 1, 2, 3, 4. But of course, today web pages don't look like this, because they are not books. They're not bound to paper. So you have the infinite scroll and so on. The same thing happened, when you transition from theater to film and so on. And I think something similar is happening now in architecture, or we are switching from manually constructed buildings to kind of completely digitally constructed buildings. And that actually means that our shapes should also change. Currently, all 3D printed houses, more or less, they look like same old houses. That's it. But this will change, or because if this technology gives us freedom to do something else, then we as architects, we have to answer to this formal freedom. And if you look at, for example, the projects of Benjamin Dillenberger at ETH and Michael Hannesmeyer at Digital Grotesque, they push this idea to the extreme. They say, okay, what happens when we have, I wouldn't say infinite, but kind of much larger formal freedom, and when we can actually build it with 3D printers, and then they build this kind of super intricate, subdivided, kind of fractal surfaces. And so these are more or less kind of formal investigations. But of course, now it's formal. But of course, nature uses form for performance. Or so somehow, if you get inspired by nature, you can use the same techniques to outperformative materials. So final example, 3D printing concretes. That is the same material, but the way we assemble concrete particles together, and the way we create these lattices, we can create concrete that is denser, less dense, porous. It can kind of let air through. We can maybe even print it in a way that it becomes transparent, or we can print it so dense that it becomes maybe very heavy, or we can print it in such a way that it becomes very strong but still very light, and so on. So, and this to manipulate, for example, concrete on such a scale was not possible before. We built a form and we would just pour concrete in, that's it. We would add some additives. So today with 3D printers, we can actually manipulate material on such a level. And this is only talking about performance. We're not even talking about shapes. Although, of course, this performance is somehow facilitated through changing of shapes. And so the big idea is once when technology gives us this power to manipulate material on such a fine scale, what do we do with it? Or do we just build the same way that we always built before? Or do we, we can create completely different formal systems where we can express ourselves and so on, and built in a ecological way, sustainable, but still very performative, but still very beautiful, but still very cheap, and so on. So this is, I think, a bit of the big idea. The way we built and the way our buildings look will just change because of this. And we have to be the ones who drive this change, or because we are not interested only in performance. As you look at, Baroque buildings that you just mentioned now, we're not talking about only performance there. Or so somehow there is something else there that is driven by, whole kind of static culture and so on. And we have to be basically the drivers of this change. But that means we have to just kind of keep up with the time. I don't know if this answered your question, but this is for me the kind of the big picture.
Any follow-up question or?
It was a very good question. Thank you very much. Thank you very much.
What's incredibly amazing with Benjamin Dillenberger's fractals is that he's not even using a visual interface, if I'm not wrong. So he's scripting the...
Of course.
And I still feel like this is taking away from a formal logic. It's still rooted in some computational idea, which is still very interesting, and yet the design, the result is left to the computer in a way. And so my question would be, okay, if we were able to build all the research that has been done in the last 15 years as in large scale, as buildings, as Gothic buildings were built, as Baroque churches were built, what would we do with it? Would we simulate Gothic churches, or would we? What would be the gain for architecture or for humanity? Or is it too big?
Okay.
For example, modernism had a very serious political agenda, and it had a societal agenda, and about equality, about living in large cities together, and so forth. What could robotics give to architecture and to the city, for example?
Yeah, question. As soon as thank you, Arthur. I will try to answer this question. I will paraphrase Professor Fabio Gramazio. So I directly take this from him. There are kind of these. I will argue for differentiation in architecture. So I think your question might maybe be reformulated. Why would we, or what is the justification that now suddenly we should sort of, kind of build in a very differentiated manner, or rather than sticking with the modernist ideal. No, everything is mass standardized, so it's cheap and it's kind of it's available for everybody and so on. So Fabio Gramazio gave these kind of free arguments for why differentiation, and I don't know if I can order them well, but the first one is, I will just put them in any order. So the first one is historical. It's maybe the easiest to argue, because we built in a very differentiated way throughout our millennium history. And somehow when we departed from that, this was in the basically 20th century. And the question is, so why do we think that, this was, or, why did this happen? And why do we think that now, by reverting back, we are kind of doing something special? Maybe we are basically just kind of going back to what worked for literally millennia before. So, and of course, there's a reason why all the buildings were differentiated. They were built by different people, different techniques, different environments, and so on. So, in that sense, through history, we see differentiation, and maybe this is just kind of going back to that. Or now, why this exists in the first place in the human civilization? That's a good question. But maybe it goes beyond this discussion. The second argument is performance, or so it may be a little bit related to this first argument. So why things are differentiated, or why it's better to build in a differentiated way, because of performance. Because if I have an environment that changes, it is very naive to think that my house can somehow look the same. If the climate changes, the insulation changes, when I have different social structures, kind of small granular families or kind of big families living together, it is crazy to think that we can, or it is, I think, naive to think that everything should be built the same way. So in that sense, differentiation basically somehow related to performance, or also all the kind of Gothic vaults, the why it has to be kind of parabolic sort of vaults, because if you want to build in a very thin way, or thin shelves, this is just the shape it needs to have, because that's how the forces flow and so on. and you know, the way that I distribute these columns, then these vaults will completely change, or they will follow certain rules, but every element there, if it's discretized, will look differently. So I cannot, you know, in order to make it super optimized, I cannot have a flat slab anymore. So somehow the second argument is differentiation because of performance. And, you know, this is a bit related to sustainability and so on, okay? If I'm in Finland, I build with wood. But, you know, maybe if I'm in Africa, I build with, you know, adobe, with kind of earth, or even with metal. You know, I definitely don't build with wood because maybe in some areas there, you know, sub-Saharan Africa, there's no wood. So I have to kind of use different ways of building. And the third argument for differentiation is maybe hardest to argue, but it goes in the direction of the kind of psychological, so let's say cultural identity. Or so we as a civilization try to somehow identify ourselves with certain groups, and we do this through, I would call it cultural proliferation. Also, we tend to invent certain things and then we tend to kind of adopt them as our own and start to see them as a part of our culture. And we then, in the future, on purpose, purposefully, we build it differently than someone else because we want to differentiate ourselves from them, or we want to retain that tradition. Not to mention that, you know, this kind of maybe idea that, you know, everybody thinks a little bit differently, so everybody wants to have a house that is a little bit different. A bit related to the mentality of people, you know. Do you want to kind of see yourself as an individual, as a bit of apart from the society, or you want to have this kind of very collectivist mentality where you say, no, we all have the same houses because, you know, we all wear the same suits, because we don't want to differentiate ourselves from each other. We want to show that we kind of work as a collective and so on. So that means there are very different needs, and differentiation can actually help here a lot, rather than that kind of we all sort of just adopt and build, you know, in the same way. And again, this is what you can see through history, how these trends and so on, as the society was changing and technology was changing, the ways of building were changing. So it is crazy to think that this will not kind of continue in this way. We just have to kind of fully embrace it. And just one final replica on the modernists. The modernists were actually very progressive, you know, because they were the ones who said, we have to, you know, we have an agenda, you know, but there's also, we have to work with, you know, they were pro-technology. They were like very technology driven, you know, like Corbusier said, we can mass produce houses, so we should, because it's going to be cheaper and everybody can afford it. And of course, there were architects who said, but what about this differentiation, the identity, you know, the ornament and so on? And Le Corbusier said, fuck that, you know, no, we, you know, we are kind of, you know, we will not think like this anymore. So I think they were kind of, it was very, very, you know, Versun Architecture. The book was, you know, was kind of showing the progression, the technological progression of, you know, cars and airplanes and so on. So they were kind of very, very technology driven. I think that somehow we would just employ exactly the same type of thinking today. We might, you know, get to, you know, I don't think we should be thinking the same way that modernists were thinking at the beginning of the 20th century, because the world's changed dramatically. And, you know, the society changed. We had 2 world wars in between. And so I think, you know, we should think a little bit different. And, you know, consumerism, neoliberalism is maybe not the way to go. It's maybe something else. Okay, I will conclude my answer here. Orkun, you can connect us again.
Thank you, Luka. I mean, I just want to quickly follow up without making a grand explanation to it. In my opinion, the answer is why not? It's curiosity. I mean, we have tools. You know, we have a 3D printer there, you have a robot there. These tools are used by everyone for making other things. Why can't you make architecture with it? Or at least you say, what can I use it for architecture, or can I use this? And I think this is what research is a little bit about, right? Most of the stuff in research is found because of curiosity. People just are rendering or putting 2 chemicals together, and then you have something. It's most of the time not based on a political agenda. Most of the time, you don't really know what you're doing. This is also the case with what we're doing. I mean, the projects we've shown are, most of the stuff that Luka has shown is actually just born out of curiosity. thing. It's really about just exploring. And if this becomes, okay, you know, somehow interesting for the industry, they anyways come to you and see it. It's also, I mean, from a very pragmatic point of view also, it's just how the world works. I mean, the construction sector is basically, you know, just like any other sector, manufacturing or services. You need innovation to stay alive. The moment somebody just becomes more powerful than you in building, like they can, for example, the Chinese construction companies can now build faster than anyone. The European construction companies are becoming less and less powerful in, you know, doing what they used to do. They used to go and build anything anywhere because they could. They had the technological upper hand. Now they are just like any other construction company. So, and then they find out that, oh, actually we need something new to stay alive. So then it becomes a mutual interest, and then it becomes more related. So it's really, I think, unlike what you said about modernism, there is, I think, not a grand political agenda. There's no, of course, people think about sustainability. If it makes sense, they include it into the mix. But I think there is a grand idea behind it, in my opinion, from what I've seen so far.
I have something to add. Can I? Okay. Oh no! Oh no! Okay. Oh, okay. I have something to add there. If you still have time. Okay. I agree with Orkun. There is kind of no grand political agenda written in the manifesto, but I think there are some things that are kind of in the background, and I'll just give you a little bit of context, and you can decide on your own if this is really true or not. You know, there is this idea that it is ridiculous that we can have, you know, cars that you can, you know, buy for, I don't know, 5,000 euros, very cheap car, used car, a new car for 10,000 euros. And the car you can never build on your own, or it's made out of actually quite expensive materials like, you know, electronics and metal and so on. But you can never build a car from scratch on your own. Another thing, you know, we have all of us have these kind of things here. And these are also something that you cannot build on your own. Also, you're completely dependent on this kind of industry, on all the kind of supply chains that make this kind of affordable, basically, for us, that everybody has one in their pocket, maybe. But someone with architecture, this is not the case. It is very expensive to build. And I don't know about you, I will probably never be able to afford a house of my own. I don't know. Academics don't get paid so much. And, you know, and the question is, why is this so? Because if I would have the material, I could maybe even somehow build the house on my own, you know, because so the question is, why is it so expensive? It's material, of course, but it's also the labor. And it's primarily because it's not optimized. Also, it's not in the construction industry is not industrialized yet. The houses are actually not so expensive, and they are cheap, you know. And if you build them out of recyclable or renewable materials like wood and so on, then, you know, we can build one house, and in 10 years you can just tear it down and build another one. The same thing we do with cars. We buy a car, 10 years, goes to scrap, you buy another one. And this sounds a little bit like kind of a super consumer, you know, ultra consumerist kind of way of thinking. But, you know, it's also a very dangerous industry to be in. You know, if you're a construction worker, you know, who of you would want their child to kind of work on a construction site? It's like saying that I want my child to work in a coal mine. You know, it's not a very attractive place to work, let's say. Also, that they're kind of trying to have less and less people there because it's hard. It's maybe, you know, kind of, you know, it's kind of a dumb job. It's just kind of physical work, and it can be done. If it can be replaced by machines, it should be replaced by machines. So kind of in the future, hopefully, we can build in a way more efficient way without people, so that, you know, everybody's safe, you know, or we have kind of people who are there are just kind of highly skilled workforce. And building is cheap, you know, so, and that's a little bit kind of this modernist ideal, kind of everybody should be able to afford a flat, but everybody should be able to kind of, you know, actually build their house. And just not to go too much into this, but, you know, you have this, with the newest kind of social demographic trends in, you know, Europe, having kind of a lot of immigrants and so on, they said, yeah, we don't want, it's almost like, if I would really have to make a kind of wild claim here, I would say kind of xenophobia is actually helping to drive this industry a little bit similar like in Japan. I hope nobody comes from Japan, because that is you need people to work on a construction site, but you maybe don't want a lot of immigrants to come in because you want to have a controlled demographic situation. But no one in your country wants to work on a construction site, so you have to kind of import people. That's probably one of the main reasons why Japan invests a lot in this kind of robotic construction, because they would rather have, of course, robots built than foreigners. And it's a little bit crazy to think that kind of xenophobia is sort of driving this development, but I see it in kind of Western or in Central Europe. This really kind of actually might be the case. You want to be less reliant on external low-educated workforce or for this industry. And yeah, the second one is, of course, the service industry. And the next thing you want kind of waiters that robotic waiters that serve us and so on. So they are kind of contemporary sociological, demographic, and economic trends that are actually sort of potentially driving this development. Or we are not working in a complete economic vacuum in that sense. Or no conspiracy theories. Right.
Yeah, thank you for the theories, Luka. Anyone else interested in?
I might have just one more. Yeah, this is more related to the position of this field of work within the career. I found very funny that from the 19th century, people was already fearing this moment. For example, Sempa said that when the oil lamps came, he said that technology was going to ruin architecture because, for example, oil lamps interrupted the facades and you cannot really watch them. And then Walter Benjamin said that in an era of reproductivity, the reproduction was going to degenerate the value of the material, not in its cost, yes, of the artwork, not in its cost, but in its somehow significance. And so today I can still not see. I still find hard to see how this new processes can find, even though they are part of architecture inevitably, because we are here at the Biennale talking about it, they can find somehow like a recognition or a valid recognition among the let's say the society of it. For example, do you see a automated production of architecture being recognized at the Pritzker? That's what I mean. So until which point do you think this will integrate to the career of to the academy, to the career of architecture as a tradition expects architecture to be? Or do you think that maybe these instruments of evaluation, such as the RIVA, the Pritzker, which is associations basically of people, they are not the best tool to evaluate this new way of producing, of building, of designing?
I like the question, but I'm just a little bit confused, because I don't see why just because we change the way we build and maybe we change the way the design, it doesn't mean that it's kind of less valuable or anything. It's definitely true that, let's say, our perception or kind of the way we value architecture in the future will have to change. We'll have to adapt. But Walter Benjamin is kind of a great example, or because he was afraid, you can just copy images, photograph paintings and so on. What will this now cause? And 100 years later, or a bit less, we still have, we have modern art, and the kind of art just redefined itself. So it's not like we don't have artists. We just, the way we understand art is different. I think architecture is actually we are even less in danger that this happens to us. That's just my opinion. And I think that we will just have to kind of value architecture differently in the future. I think architects, we as people, we will never be excluded out of the equation unless we cause this on ourselves. Also, Again, I don't want to be very pessimistic in this lecture, but you know, I was in some BIM conferences, and yeah, you know, I was invited, you know, to talk there and so to participate, and sometimes I would not see a lot of architects there. There would be a lot of engineers, you know, data engineers, I don't know, construction management people, but very little architects. Also, I'm kind of, I was even a bit afraid. I was thinking like, shit, you know, this. It's not like I don't want these people to work, but it's somehow, it's kind of, at least in the field of BIM, it seems as architects, we as a profession are just underrepresented. And of course, these big companies, you know, as they switch over to BIM, it might be that, you know, people that they then employ are not architects, you know, so that, and this, of course, our fault. Also, if we don't engage with these new technologies, we will be just left out of the conversations. And I think in China, this maybe a little bit happens, you know, you have kind of huge companies that build, but the question is if they have any architects there. You know, of course, there are some Chinese architects that are very, you know, that also won the Pritzker and so on. But I think I'm not super familiar with the situation. But I think even if you ask them, they would say somehow like they are rather an exception than the rule. Or I think our biggest, I think the architecture itself or its value will not diminish, but it could be that we as architects, as a professional, we just have to kind of, we might somehow die out, or and if we make ourselves irrelevant, or so I'm more hopeful for architecture in general, but less hopeful for the profession as such. Yeah. I don't know if this answers your question, but this is the best that I could do. Yeah. Yeah. And I mean, you are the flag bearers. I see you're quite young people there. So, I think the more there are of you, you know, kind of having a proper mindset and going into offices, you know, forming your own offices with the proper mindset, you know, then I'm not worried. Then I'm not worried at all. I'll just have to say again, I don't want to bitch about people, but you know, we visited the Peter Zumthor at one moment. And of course, he's a very distinguished architect, but, you know, also very old. And, you know, he would talk about using computers, you know, in the work. And, you know, his problems are, you know, he talks about now the scalelessness of these architectural drawings, or the fact that you can have a drawing that doesn't have a scale because you can zoom in and zoom in and zoom in. And you can very quickly lose the scale, whereas when you have it on the paper, you know, you cannot zoom in. You have this kind of, at least the traces on paper that you can identify, they always relate to a scale. And he saw this, for example, a big danger for architects working on a computer. And this is, of course, the discussion that we had in the 90s, but I don't know, like, I'm not so sure if this is really relevant today, you know, to talk about this, you know, maybe it is, but it's somehow, I worked as an architect a little bit, and I never saw this problem of kind of losing the scale on a computer. So, you know, it could also be that some discussions that we have today, in 10 years, they will just become irrelevant, or not necessarily that the problem is solved itself, but that when you have intelligent people and creative people doing things, you know, that they will, you know, invent new ways of doing things. They will not do it wrong. They will just do it in a kind of way that is more appropriate to the medium. Yeah, and we should kind of be these people, you know, that drive this thinking forward. Also, a lot of CAD software was not designed for architects. It was designed for mechanical engineers. For example, Rhino was designed basically for mechanical engineers. And this I see as a big problem, more because we're using the software that was not designed for us. Maybe you can say, well, ArchiCAD was designed for us. Yeah, yes and no, you know. So it's kind of we have to be on the forefront of this development, because we want to develop our own tools, or we want tools to be developed for us, not the other way around. We don't want to use tools that were developed for someone else. That, for example, AutoCAD also was not designed for architects. So, you know, we have to be very, very careful in relation to the tools that we use, you know. I'm teaching here architects and architecture students, and, you know, I'm very reluctant to use Revit, because, you know, at one moment when the student comes and starts to pull in stuff from a catalog, I get very, I see this as a big problem. Or so, you know, so it's kind of you have to be aware of the tools that we are using. I'm finishing my answer here, Orphan.
Thank you, Luca. There's another person. We should probably stop it here and let our students see the rest of the Biennale. But many thanks for joining us. I think it's been a great contribution, and I hope you all enjoyed it. We'll see you. Are you planning to come here to the Biennale this year, or have you seen it already?
No, I haven't seen it. No, I haven't seen it. I'm somehow a busy man, but I will try to come in summer toward autumn and so on. Yes.
Great. And then make sure to stop by the Turkish pavilion because
definitely.
Cool in many ways. Also, yeah. Okay. Well, thank you and.
Thank you very much, and I'm off to sauna. So you enjoy Giardini. I will enjoy finish summer.
Enjoy the sauna.
Cool. Ciao, guys and girls.